Welcome to Introduction to Data Visualization Part 2, Encoding, where we'll talk about programming data visualizations in Python. My name is Kendra Audig, and I'm a PhD student in J.B. Pauline's lab at McGill University. In Part 1 of this lecture, we talked about decoding, and I'll just go over the difference here again. Decoding happens when someone sees your figure and understands something about your data. Encoding happens when you write code to create the figure according to your plan. In these lectures, I hope you will learn to use principles of visual encoding and decoding to efficiently create visualizations that are effective and reproducible. Understanding decoding will help you make effective figures, and understanding encoding will help you make figures in a way that's reproducible and efficient. In order to program a figure efficiently and reproducibly, it's helpful to understand some computer graphics, that is how the computer makes a figure, some Matplotlib basics, what you and Matplotlib need to do to make the figure, and a little bit about higher level libraries in order to make more complex visualizations. Before getting into these topics, we're going to start by making a really simple chart in Matplotlib. If you're completely new to Matplotlib, don't expect to understand the code right away, as we'll continue to unpack it as we go through different topics. In the last lecture, we used principles of decoding to create this plan for a figure. Now let's see how to encode this figure in Python. So the first thing I did is open a new file in VS Code and save it as makinggenderbarplot.py. First, I'm going to import Matplotlib, this sub-library of Matplotlib called pyplot as PLT. And I'm going to start a blank figure with an axis on it by calling subplots. Now we only want one subplot here, so that's the number of rows and columns of subplots. And say we want the figure size to be 3,3. Okay, so what I usually do next is actually save the figure so that as I run the code, I can see what's going on and keep it open as I continue to run the code. So I'm going to do fig.save fig and then enter the file name. So now we briefly have to jump back into more basic Python and remember that it's not good to hard code paths. Like if I started with the root of my computer and went on, it would always work no matter where I was on the computer, but it wouldn't work on other people's computers. So let's, or it would end up in unexpected places. It wouldn't be able to find that directory, and if I use a relative path, it could end up in unexpected places depending on from where they run the Python file. So I'm going to, from pathlib library, import the path object, and I'm going to define my path using this object. So figpath equals path. So this just means resolve the path of the current file. From there, I want to go to my parent directory so that it's in the same directory as this one. If I wanted to go further up, I could do parents and select how far back I wanted to go, but I'm just going to go in the current one. And then I'm going to call the figure making gender bar plot, and I'm going to make it a PNG file. So I am saving the figure, and it should show up here in my current directory. Oh wait, no, I gotta, oh, it's supposed to be fig size, not figure size. Thank you, VS Code. And here it is. So I'm gonna open the plot below this one just so that we can see all of them at the same time. So we want to plot, but first we need to have some data. So let's see, on the x-axis we're going to have male and female right here. On the y, we need two numbers, one for this bar and one for this one. So this one is 396, and the female bar goes up to 51. So now we can use the helper function from the axis object for creating a bar plot, and all this will make more sense later when I explain these different things. So we're going to do the first argument is x, so we're defining x equals x, we just called it that. The next argument is height, and you can see that VS Code is helpfully telling me what to enter. So the next is height equals y. And that's all you need to make the basic bar plot. Yay! Okay, so now let's add this y label. It didn't add anything there, so we can do x set y label and then n. Let's run that and see what happens. Oh no, we can't see it, so we don't know if it's there. The problem is these are the basic elements of the plot, and right now it's only saving what I defined as the figure size, so if anything is being drawn outside there, it's not showing up. And the way to resolve that equals bbox, I think it's bbox inches equals height. And that will just adjust the layout so that it all fits. There we go. Now the n is rotated, so let's rotate that. By default, the y label is rotated 90 degrees, but we want it, I think it's rotation, might be orientation. We want it at 0 degrees so that it's facing up. Yay, there we go. And if I want to hack it so there's a little more space between the 200 and the n, I could just go like that. Just add some literal spaces there. Nice. Okay, so now what about the colors? Well, actually we can set the colors right in here, right in the bar helper. So we can do color equals and then a list of 2 colors, but let's define it up here just so that we can see things consistently. Okay, so the first color we want to be blue. The second color we want to be pink, and these are named colors that Matplotlib will recognize. Nice, so it's working. It's not quite the same shades as we want, but the basic colors are there. And we also had a black outline here, so we can do edge color equals k, and this is just another way of defining colors in Matplotlib. There's some short forms for really basic colors. There we go. So say we actually want the exact colors we planned. Well, I could open it in Inkscape and look here and see what the fill color is and select the RGBA hex code. So let's go back here. I'm going to put a number sign so Matplotlib knows it's going to be a hex code. Go back here. And this is another way of defining color, and we will explain all this later. It's just a really quick demo so that other things will make sense in context. Wow, that's pretty close. I think that's good enough for now. And now we'll go through different aspects of encoding so that hopefully by the end you'll understand why I did all of these things. So now that we've seen a little bit of code and maybe have a bit of intuition about how this is going to work, we can look in more detail into computer graphics. First, let's start with something that's probably familiar to most of us, some common file formats for images. One of the main defining features of each is whether they are constructed from mathematically defined shapes, like this vector image here, or from pixels, like this raster image here. The obvious difference between these types of figures is that when you zoom in, like we have here, on a raster-based image, it looks blurry. You can see how the pixels make it look blurry. But vector images are just as clear no matter how zoomed in you go. Generally, vector-based images are better if you want a good quality image in, say, a paper and a slideshow and a poster. It'll look just as clear no matter what size people need to see it from. But the figure is very complicated, If the figure is very complicated, then the SVG file can become very big because there's a lot of equations and details that need to be stored. To understand why these types of files are different, we need to briefly think about how images are constructed on a screen. So this is a cathode ray tube, or CRT, and the complicated insides are not important for our discussion, but the main thing to take away is that there's this electrode gun in the back of a screen that shoots electrons at the screen that we see, and this is what creates images on a screen. Electrons. For a vector graphic, the electron beam creates images by tracing the vector equations. So in the bolded arrows here, you see where the cathode ray tube would be shooting electrons. This is the path of the electrons, and then it would not shoot electrons and start again here, and so on. For a raster image, the beam scans across each row to create pixels on the screen. So you can see that if we zoom in, these squares are going to be bigger or smaller because it always follows these same paths, whereas here, because it's tracing the exact paths instead of making little squares, it'll still be clear no matter how zoomed in we go. So now, just to give a little demo, I'm going to go into VS Code, which we saw before. And here I have the PNG. I'm going to save it as a SVG, and it's just as simple as changing the file extension. And something really interesting is if you try to open a SVG in a text editor, it'll actually show you all the equations and details that go into creating this image. Let's zoom in, zoom in, zoom in, zoom in, zoom in. See, we've zoomed in really far on the SVG, it's still clear. If we zoom in really far on the PNG, oops, you're seeing the blurriness. Here are a few more differences between these file types. We won't go as deeply into why they're different, but it's good to know this so you can choose the best format for your data visualizations. Only PNG and SVG allow for transparency. GIF, PNG, and SVG all allow you to create animations. The GPG is lossy, which means you're losing information, but GPG has a lot of different options for colors, and so it's good for things like actual photos. Now let's talk about color again. We've already discussed how color can be useful for encoding shapes and patterns and groupings in the last lecture. And to round off that discussion, let's see how a computer makes color. I'm going back a bit further in the process of color perception because I find it fascinating that both computers and our photoreceptors use red, green, and blue as the basis of color. In the back of our eyes are photoreceptors that respond preferentially to light at different wavelengths. So here you see the preferential spectrums for these three different receptors. Let's move up to cognition. We usually talk about color as hues, as named colors. Like in the last lecture, we learned in order to cover the full range of colors, we need to also discuss saturation and luminance, and this is the HS Love palette. And in particular, this one has been corrected for uneven perception of lightness over the hue spectrum, and we talked about that in the last lecture. But a computer goes fully back to the basics, producing color through beams of electrons with frequencies in the red, green, and blue ranges of the spectrum. So here's the cathode ray tube again in a different visualization, showing that there are three different electron guns. There are three different kinds of electron guns for the different primary wavelengths that are transmitted. And the images are created up of different mixtures of these wavelengths. The RGB palette can be thought of as a three-dimensional space where each color, including its hue, saturation, and lightness, is made up of different amounts of these three frequencies. This can be visualized in a cube. I find this really fascinating that the three electron guns of the three kinds of electron guns match up with the three kinds of cones. But this way of thinking about color is really not intuitive, And let me just demonstrate this in Inkscape to show you how it works. So here we are in Inkscape looking at that RGB color cube. I have the main RGB axes bolded, and you can see red is at 100. So if I look at this colored box and put the red at max, so here the scale goes up to 255, but this is essentially like the 255, but has been normalized between 0 and 1. So you see red, when the red is at full and the green and blue are at 0, the color is red. So these three are pretty obvious how they work. However, if we look at something like yellow, we have 1 in red and 1 in green and 0 in blue. So let's do that. And then it gets even more intuitive when we have unintuitive when we have colors in between these points on the square. So the color orange is going to be approximately between red and yellow. And if you just look at these scales and the colors here, you can see that it's not super intuitive how saturation and lightness is generated. So if we want a dark green, we have to add some red to the green. Yeah. And so I encourage you to find something like this and just play around with it to see how it works. Another thing this is useful for is showing how the hex code for the RGBA color scheme is defined. So as I go up here, you can see this number is changing. Now it's at 5, 6, 7, 8, 9, A. So this is in hexadecimal, so after 9 comes A, and it goes up to F, and then goes up to, and then shows 10. So that's the hexadecimal way of encoding the RGBA colors. Now once you know the color you want to use, you can indicate to Matplotlib which color you want to use using RGB or RGBA. Alpha stands for transparency, and you can see they've scaled things between 0 and 1 as well. Or you can use the hex of RGB or RGBA with a number sign in front of it. And you can look at this page and see a lot of different ways that you can enter colors. For example, you can also, for many colors, just call them by their name, like red. And then internally Matplotlib will translate that. If we enter colors by name or with a hex in Matplotlib, it will still encode them as RGB behind the scenes. So we can see that if we go in here and run the code, and I'm just setting this breakpoint here so that we can jump into the variables at that point. And if we go to the axes and then look at the containers, we'll talk about a few of these different things later. And we look at this bar container and the first rectangle object, so that's going to be the blue one. Let's look for face color, and you can see that it's encoded with 3 values. You can R, G, and B. Even though we indicate it with the hash, it's recognizing it as RGB. Now let's go over some Matplotlib basics. Matplotlib is a Python library for creating visualizations. We're going to go behind the scenes a bit to look at how it works. The important thing is to remember what you have to do, but I hope that it'll be easier to remember what to do and which help to follow if you understand a bit about what Matplotlib is doing. If you've ever used Matplotlib and ever looked up how to do something, you might have noticed that there's usually more than one way to accomplish your goal. So here's somebody asking on Stack Overflow how to add a Matplotlib legend. In one of the suggestions, they said to use the command ax.legend. And in another suggestion, they said to use plot.gca.legend. These differences reflect the different coding styles in Matplotlib. There's an explicit and an implicit coding style. The explicit style is object-oriented and is the most transparent way of interacting with Matplotlib because you're directly or explicitly interacting with the objects. The implicit style is much more similar to MATLAB. It can do the same things in most cases, but you don't interact directly with the objects. So here are two pieces of code that create the same figure. We can see the differences if we focus at the beginnings of these lines. In the explicit style, they define an object called ax right here, and then they adjust it explicitly in the following commands. In the implicit style, they continue to call the pyplot sublibrary, which then they adjust implicitly. So behind the scenes, the pyplot library is keeping track of which objects should be changed by these commands, whereas in the explicit version, you're interacting directly with them. Let's take a closer look at the important objects here. The fig variable is an instance of the figure object. It's the top level container for all elements of the plot. The ax variable is an instance of the axes object. It's a subclass attached to the figure, and it includes all the elements of an individual plot. Both the figure and the axes objects are from the artist base class, and an artist is something that uses a renderer to draw on a canvas. Stepping back a bit, there are three main layers of the Matplotlib API. The figure canvas is the area onto which the figure is drawn. The renderer is the object that knows how to draw on the figure canvas, so you could think of that like a paintbrush. The artist is the object that knows how to use a renderer to paint on the canvas. So you'll be working with the artist object most of the time. There are two main types of artists, primitives and containers. Primitives are basic graphical objects, so they're things to draw. This includes lines, rectangles, text, and images. Containers are the locations of where to draw the rectangles. So this includes the figure, axes, and axis subclasses. Here we have an image of the anatomy of a figure, and we're not going to talk about everything on this figure yet, but I just wanted to show, it nicely shows here that the figure is this entire area, whereas the axes are just this area within the axes where we are drawing the plot, and it includes the two specific axes, which are instances of the axis object. So it's a little confusing because it's all axes and axis and axes and axis. But axis is one of these axes, and axes is this entire area, basically. So what actually is an artist? Seems like an artist can be almost anything. The actual definition is an abstract base class for objects that render into a figure canvas. So we already talked about rendering and the figure canvas. Typically, all elements in a figure are subclasses of artist. So like everything's an artist. And I was trying to understand this inheritance diagram for the artist class. You can see the artist class here, and there's just so much complication and so many different things that an artist can be. So long story short, for our purposes, it's artists all the way down. Again, most of the time you'll be interacting with artists. On the axes artists, there are helper methods for different plot types. For example, the line and bar graphs, or for showing an image or a heat map. This is really helpful, hence the name helper method, so you don't have to construct figures from basic shapes and lines. There are also helper methods for customizing charts, so you've already seen this figure briefly, but now all these other things are for further customizing the specific chart type you've chosen. Remember, this is the explicit way of coding, where you're interacting directly with the axes artist objects. So this AX is a variable that's an instance of the axes artist. Here we see a Matplotlib cheat sheet. I know it's way too busy to be on a slide and be understood, but I just wanted to introduce you to it. It can be found in their documentation, And here I've highlighted where you can find the different plot types and the advanced plots. And then they also have the anatomy of a figure here, but if you look real close or zoom in on on a version you open in the internet, you'll see that it's just giving the labels and not the actual commands for changing them. But here are some of the commands, and it's pretty intuitive what each one does. So here we are back in VS Code looking at the Python file that we made before to make our figure showing the gender differences in the abide dataset. And we're just going to run the code in the debugger with this breakpoint so we can have a closer look at some of the variables in sort of an interactive way. So here you can see we defined fig and ax. This is a figure class, and this is an axes class here. And here we use the helper on the axes class to create a bar chart. And this helper method knows, for example, that it needs to create rectangles for the bar chart. So if we go in here, look in here, scroll down, let's see containers, you see the bar containers. And let's go in the first one. And here you can see two pouches that are rectangles, and which makes sense because in our bar chart we have two rectangles. So don't expect to understand everything in here. I just wanted to give you a bit of a glimpse of how what you're coding here is turned into more simple kinds of objects like rectangles and lines, etc. So now we're going to do some live coding to replicate this figure that we saw in the last lecture. It's a good example because it involves a basic kind of plot, but with multiple categories, and it involves customizing a few different aspects of the plot. So here I am in VS Code, and this is a fast screen recording. I'm just voicing over it. So I've imported matplotlib flyplot library. I'm initializing an empty figure and axis object, and I'm going to save the figure. In order to that, I need the fig path, and in order to do that well, I need to import pathlib, or that's one way to do it well, so that it can be run from anywhere on my computer, and it can be run on different operating systems. Here I'm just giving the file a name, and I'll enter that into the savefig method, and then I can open the figure and put it here. Now I can compare the two. Now I'll just put some comments in to define the places because this file is going to get longer. So now I'm going to define the data, and I'm just stealing the data from the figure itself. Each line has an equation, and so it's really makes it easy to draw. That's why I chose this one. So I'm just taking this information from the labels on each line in the figure. Okay, so now I can define the function that's going to take in the physical intensity and output the perceived sensation. So basically defining how I'm going to calculate each line before I can plot them. So here I'm calling the function Stevens law. As input I'm taking intensity and n. I have written out the equation and return sensation. So now in order to create the lines, I'm going to use NumPy. I'm going to make the x values by going from 0 to 5 at steps of 0.1. And for the y values, I have to calculate them for each of the data items. So here I'm looping through each label and n in the dictionary data that I created, and then calculating the y coordinates for that equation and appending them into a list. So now let's see if I can create the plot. I'm going to use x.plot for a line plot and try plotting the x and the y's. Oops, so here in my own function I forgot the variable n, so I entered that. And now x and y must have the same first dimension, so I can only plot one y at a time here. So let's put it in a loop over all the y values. There we go. But the y limits are quite different, so it looks quite different. So let's set the y limit from 0 to 6. Even though it stops on 5 on the labeled axes, it actually goes higher than that, so I'm choosing 6. There we go. Right, I'm changing it to 5.1 because NumPy Python only goes up to 1 less than the final value because it starts at 0. Here I'm defining some colors, and I'll also loop over those colors in order to input the colors for each line. So I'm using zip to zip through each of those lists and inputting the color, and let's run it. And here you see, here you see the approximate colors. The original ones, sorry, they looked a bit funny to me for a second there. So here I'm also going to zip through the stimulus label and the value from that dictionary so that I can enter the label. So here I'm defining how I want the label to look. I want the stimuli and then in brackets the number n, just like it says there. And the simplest thing is to just add it as a legend. And if I was keeping the legend, I would put it outside of the axes box, obviously. But now let's copy what they actually did and add the text right next to the lines. So for that, I need the locations for each bit of text that I want to add. So I'm looking approximately, I'm adding plot.show so that when I run it, a figure will show up. Oops, okay, I forgot. Alright, I had to comment out that one. So here, when you do plot.show on the figure, you can see at the bottom of that figure the x and y values for where your mouse is. So that's really handy if you want to annotate something. You can find the locations approximately of where you want to annotate. There, now I've got all the approximate locations of where I want these text annotations to be, and I want to also zip through these, and I'm putting them in brackets because I want to get each tuple, I want to get each individual value in the tuple. So I want the text at the location x and y, and I want the string to be the label, and let's get rid of the legend function. Oh, why? Oh, I made a spelling error, so let's correct that. There we go, y text, not y yext. And now I'm getting another error. Oops, instead of backspacing that whole thing, I accidentally just put it on a new line. There we go. And there's our text. Obviously, this isn't good enough. We want to have the rotations as well. Let's just clean up this code a bit. And let's define the rotations. So I'm just kind of eyeballing it here, looking at each line on the original plot and estimating what the angle is once the line gets straight. And so I also want to zip through the rotations, so let's add that in the loop. There we go. Now the labels are roughly rotated. It's not perfect, so let's just go in and adjust it approximately again. We can adjust the locations and the angles. Here I'm adjusting some of the locations, and here I'm adjusting some of the angles. Let's see how that looks. Okay, that's pretty good. They're all legible. We won't get too picky for this. And let's color the text by the color of the lines. Perfect. So the text is going beyond the confines of the figure, so we're entering VBox inches equals tight in the save method, save fig method, so that it accounts for that. It's showing everything that we put on it. Now we're going to get rid of the lines on the top and the right side of the figure, just as the original figure has. And then we're setting the Y label to be perceived sensation and the X label to be physical intensity. And let's set the title to Stevens Psychophysical Power Law, and you can put text in Matplotlib labels using the $ and LaTeX type equations. There we go. And I'm just adding some new lines under the title just to give it some more space. Playing with the figure size. Let's see how this looks. Okay, everything is there. Maybe it's all a little bit small. Let's make the figure a bit smaller so that the text will be bigger. It's kind of a hacky way of fixing the font size. And let's fix this typo. And that's pretty good. Let's try it even smaller. See if we can get the text a little bigger. Trying a non-square layout. Nope, that messes up my angles. Let's get back to the square layout. No, that's too squishy. Let's go back to 3:3. And let's put them side by side. Zoom in a bit. All in all, that's pretty good. I could spend more time picking the colors, but I think that's a pretty good match. Now, very briefly, we're going to look into a few higher level libraries. First, we have Seaborn for statistical data visualization. So it's a Python data visualization library based on Matplotlib. So you can still edit Seaborn plots with Matplotlib. And it provides a higher level interface for drawing attractive and informative statistical graphs. So a few features that will be useful to us. It works really well with the pandas data frame that you learned about a few days ago. The default colors are from perceptually uniform color palettes, which is very admirable. It can actually calculate statistics as well as do visualizations, so it can make your coding pretty efficient. And it more easily visualizes complex data, like multivariate data. So I'm not going to go into the syntax too much. It's pretty self-explanatory using the documentation, and I want you to be able to practice in the tutorial after this, go into the documentation to see how it works. The next library I'm just going to mention is Nylearn, and it is a really great tool for plotting brain images in Python. You also were introduced to it yesterday and probably saw a few figures from Nylearn. So part of the tutorial is going to be actually going through one of the examples on Nylearn to explore their different plotting functions. So now we come to the end of the second lecture where we talked about encoding, and we talked about how to program a figure efficiently and reproducibly. We should understand some computer graphics, some Matplotlib basics, and a little bit about higher level libraries so we know when to use them. Thanks so much, and I hope you learned something.